In this video, we're going to take a look at case 2 of finding the area, and we're going to use horizontal cross-sections this time. Now, suppose the region is bounded on the sides by two curves. We're going to call them the left side and the right side, and it's going to be bounded on the top and the bottom by y equals d and y equals c. So think of dividing the region up into horizontal rectangles this time. Now, the reason we want horizontal rectangles is because the curves are on the left and the right side instead of on the top and the bottom. Now, the height of this typical rectangle is not going to be the top minus the bottom. Because the rectangle, I guess I could say, is lying down, we're going to use the right side minus the left. So it's going to be the right curve minus the left curve. And the thickness this time is going to be vertical. So we're going to call that thickness dy. So the area of a typical rectangle is going to be A equals our height, which is right minus left, times dy, which would be our width, our thickness. To find the total area, we're going to integrate so that we can add up all of the area of these little rectangles. This will give us A is equal to the integral from C to D of right minus left times dy, which is now equal to C to D. And instead of using right and left, I'm going to say that this is going to be f of y minus g of y and then dy. Now, this time we're using dy, and the dy in the integral reminds us that I want right and left, the right expression and the left expression, to be written in terms of y. So notice it's f of y and g of y instead of f of x and g of x. Let's take a look at an example. So I want you to find the area of the region between the curves y equals x minus 1 and y squared equals 2x plus 6. Now, the x minus 1, we're going to graph that as a line. So starting at -1, and then it has a slope of 1 as well. Now, for this parabola, I'm going to rewrite it so that it's a little bit easier to see. So I'm going to go y squared minus 6 equals 2x, and then divide everything by 2. So I have x is equal to half y squared minus 3. So this is going to be a sideways parabola, and the vertex is going to be reversed as well. So this is our x, and this is our y. So this would be our h and k, so it'll be -3 and 0. So that will be here. And then we can plug in y values to get our x values. So if I plug in plus or minus 2 for my y, I'm going to get -1 to be 2 and -1 to be -2. If I plug in, so there's one more point that I can check here, is what happens when I plug in 4. So 4 squared is 16. 16 divided by 2 is 8. And then 8 minus 3 is 5. So I have an x value of 5 and 4, which is there. And knowing that the parabola is symmetrical, I should have a point down here. So I get a parabola that looks like this. Oops, a little bit off there. And the parabola looks like the bottom half is like that. All right, now, if we want to find the area, if I did vertical cross sections, I will have a different curve as we cross -2. So from -3, sorry, not -2, from -3 to -1, I have a top parabola and a bottom parabola. But then from -1 to 5, I have the parabola on the top and a line on the bottom. So if we do it this way, I'll have to add up two different integrals. So if I draw horizontal cross sections, you will notice that my left side always touches the parabola, and my right side of these lines always will touch the line. So by doing this, I need to only use one integral, which I think will be a little bit easier. So we're going to find the area, and our y values will be from -2, our lower limit, to our upper limit of 4, which we can see from our picture. And if you didn't draw the picture, you can also solve this by substitution, or maybe even elimination. Elimination might be a little bit more difficult. So it might be easier to take the x minus 1, plug it into y, and then solve to find -2 and 4 to be your upper and lower limit. All right, so then we have our right side, which is the line. Now remember that we have to use and rewrite our expressions so that they are in terms of y. So we can see that this one is not yet. So we need to move the 1 over. So now we have y plus 1 is equal to x. So therefore, my right side is going to be y plus 1. And then my left curve is going to be half y squared minus 3. And then dy. All right, so integrating by hand. Actually, you know what? Before we integrate, let's join everything together. So I'm going to have -1/2 y squared, and then plus y, and then 1 minus -3 is 4. All right, let's actually integrate this. Might be a little bit nicer. So we get -y cubed over 3, and then times that 2. So we get 6 plus y squared over 2, and then plus 4y. And then we're going to integrate from -2 to 4. So plugging this in, I'm going to get -64 over 6 plus 16 over 2 plus 16, and then minus. So we have a negative, so it's going to be positive, so 8 over 6 plus 4 over 2, and then minus 8. All right, so we get -64 minus 8, so that's going to be -72 over 6. And then this is actually 8, so plus 8 and 16, so that's going to be 24. And then 2 minus 8, that will give us -6, but we have that negative, so we're going to have plus 6. So joining all of this together, -12 plus 24 plus 6 is going to give us 18 units squared. All right, so in summary, if it's easier to use horizontal cross sections so that we only connect one curve to another curve, then I would recommend doing horizontal cross sections. But if there's only one curve and one curve below on the top and bottom, then you can use vertical cross sections.